Hello my friends. So, now we are going to start our new chapter on testing of composite materials. So, before going to start this particular chapter, just let us know that what are composite materials. So, basically as a layman I can say you that it is a nothing but the mixing of different materials and just to make a composites. So, generally the composite materials are the multiphase materials with measurable fraction of every phase obtained by artificial combination of different materials as per our requirement. Generally we are varying different weight percentage over there, so as to attain properties that the individual components by themselves cannot attain. So, suppose if I take a aluminum composites, so simple aluminum or maybe the virgin aluminum cannot gives that kind of properties, but when I am adding maybe the silicon carbide or maybe the alumina, so it can give you a better properties. Generally the aluminum composites we are using for the aerospace applications. Composite materials are not by the byproduct of any chemical reactions between two or more of its constituents. So, there are two major components in a composites. First one is called the reinforcement, either it may be discontinuous or maybe the dispersed phase materials that provide strength to the matrix, and matrix another one is called the continuous phase materials that holds the reinforcement in place. So, generally the matrix plus reinforcement is known as the composite. Now, what are the role of matrix and reinforcing phases? Matrix in a composite material, the matrix material serves the following functions. First is called holds the fibers together, not only the fibers, if any kind of nanomaterials also nowadays we are using. So, it is holding any kind of additives or maybe the fillers, generally you can call it, protects the fibers from environment, distributes the loads evenly between fibers so that all fibers are subjected to the same amount of strain, helps to avoid propagation of crack growth through the fibers by providing alternate failure path along the interface between the fibers and the matrix, enhances transverse properties of a laminate. Generally the classification of matrix materials like metal, polymer, ceramic. And what are the reinforcement? The role of the reinforcement is to strengthen and stiffen the composite through prevention of matrix deformation by mechanical restraint. Classification of reinforcement, like as I told already, particles, fibers including whiskers or maybe other shapes. Examples generally for naturally occurring composites like bone, collagen fibers embedded in hydroxyapatite matrix, wood, cellulose fibers held together by lignin matrix. So, from this particular image you can understand man-made composites. One is called the reinforced concrete, steel reinforcing bars embedded in the concrete. Generally we are using it for the structural applications for making any kind of buildings, structures, pillars. Fibers composite, variety of fibers like glass, Kevlar, carbon, nylon, etc. Nowadays we are using the Kevlar fiber for aerospace industries. We are making the Dreamliner or maybe some Boeing bound together by a polymeric matrix. And last one is the cermets, it is nothing but the combinations of ceramics as well as the metals. Composite materials composed of ceramic and metals, so it is known as the cermets. So, here we have given all the examples of the wood structure, then reinforced concrete, then fibrous composites, it is some kind of sandwich like structure, then cermets as cutting tool materials, we are using it as a insert. Classification of composite materials, the composite materials are commonly classified based on the types of material or reinforcing material structure. So, composite materials based on matrix material, metal matrix composite, polymer matrix composites and the ceramic matrix composites. In short we are calling it as MMCs, PMCs and the CMCs. Based on reinforcing material structure, it is particulate composites, fibrous composites and the laminate composites. Now, classification based on matrix material. Based on the type of matrix material used to fabricate the composites, they can be divided into three categories. As I told already, metal matrix composites generally we are calling it as a MMCs, polymer matrix composites we are calling it as a PMCs and the ceramic matrix composites generally we are calling it as a CMCs. First, what is metal matrix composites? They consist of fibers or particulates surrounding by a metallic matrix. Most metals and alloys can be used as matrices and they require reinforcement materials to be stable over a range of temperature and should be non-reactive too. Processing of a metal matrix composites tends to be much more expensive than that of a polymer matrix composites due to high processing temperature required. So, I can give you one best example in we are using these composites from our ancient age is called the, generally we are using it in village sites for making the house and all these things. So, we are taking the clay and then we are adding the straw over there. So, now clay is the matrix and whatever the straw I am adding, that is known as the reinforcement, and we are using it for making the house or maybe the floors or this kind of things. So, it is coming from very old age. Most common constituent materials used in this category are matrix materials like aluminum, beryllium, magnesium, titanium, iron, nickel, cobalt and silver. Reinforcement materials like silicon carbide, Al2O3, B4C, TiC, TiB2, tungsten, steel fibers, graphite and a number of other ceramics. That actually depends upon which type of property we need. If we need the hardest materials, so we are going to add some tungsten over there or maybe B4C or maybe some other materials like silicon carbides. If you need some materials which can hold the temperature, high temperature, if we need some materials, if we need the high electrical conductivity. So, as per our requirement we are adding different types of fillers. Factors affecting properties of MMCs like type of metallic matrix, reinforcement materials, reinforcement morphology, reinforcement volume fraction, orientation, matrix alloy compositions and the heat treatment. So, generally what are the applications? We can use it for the diesel engine pistons, cylinder liners, brake drums and brake rotors, connecting rods, piston pins and the drive shafts, but here we have given a very limited number of examples, but we are using it these metal matrix composites for n number of applications. If we talk about the polymer matrix composites, so generally it is composed of a variety of short or continuous fibers bound together by an organic polymer matrix. They are very popular due to their low cost and simple fabrication methods. Based upon the type of polymer matrix, they can be further classified into two parts. One is called the thermoset composites, another one is called the thermoplastics composites. Thermoset polymers are used as matrix materials which once cured into a solid form cannot be returned to their original uncured forms. The best example is the natural rubber or maybe any kind of rubbery materials. So, if we give a particular shape to that particular rubber, then after that we cannot return back to its original positions. Generally polyester, polyurethanes, epoxy are the examples. But when you are talking about the thermoplastic composites, generally different types of polymers. So, we are giving a particular shapes, then after maybe melting it or maybe some kind of load or pressure, again we can give it another shapes also. So, thermoplastic polymers which can be molded, melted and remolded without altering their physical properties are used as matrix. What are the examples? Polyethylene, polypropylene, polyvinyl chloride, etc. What are the applications? We are using it for the aerospace and military aircraft, automotive industry, constructions, medical device and there are also so many. What are the drawbacks? Environmental degradations, yes, of course, nowadays we are seeing that the using of the plastic carry bags is a really threat for us because it is not biodegradable, it is making some kind of toxic gases or it is a one kind of hazardous materials. So, recycling is also it is very difficult. So, that is why it is not good for the environmental point of view. Next, moisture absorption from environment causes swelling in the polymer as well as decrease of glass transition temperature. Generally TG is known as the glass transition temperature. The moisture absorption increases at moderately high temperatures. These hydrothermal effects can lead to internal stress in the presence of fibers in polymer composites. So, if you see we are using some kind of polymeric materials, after certain time it can change its shape and size. A thermal mismatch between polymer and fiber may cause cracking or debonding at the interface itself. So, if you see some old tires, you can see after certain time the rubber is coming out from the steel bead or maybe the nylon cord, that is nothing but the debonding in between the matrix as rubber with the filler like the cords or maybe the steel cords or maybe the nylon fiber. Next come to the ceramic matrix composites. These materials are those in which one or more distinct ceramic phases are intentionally added to another in order to enhance some property that is not possessed by the monolithic ceramic materials. So, a single ceramic or maybe a virgin ceramic cannot provide all the good properties. So, just to enhance the other properties, we are adding different type of reinforcements over there. Basic reinforcements which are included in the ceramic matrix are carbon, glasses, glass ceramics, oxides and the non-oxides. Ceramic matrix composites overcome the major demerits such as brittle failure, low fracture toughness and limited thermal shock resistance of monolithic ceramics. Processing temperature of CMCs is extremely high compared to polymer or metal matrix composites, which leads to a very difficult and expensive processing. What are the applications? Heat shield system for the space vehicles, components for high temperature gas turbines, brake disc and the brake system components, slide bearing components. That means, where the operating temperature is more, we can use this kind of ceramic matrix composites. Next, classification based on reinforcing material structure. There are different types of reinforcement that go into the composite materials like fibers, particulate, whiskers and layers. So, on the basis of the structure of the reinforcing material, composites can be broadly classified into 3 parts. One is called the particulate composites, fibrous composites and the laminate composites. What is particulate composites? Particulate composites consist of a matrix reinforced by a dispersed phase in the form of particles. So, small particles. If it is in nanometers range or maybe the size, we are calling it as a nanoparticles or maybe the nano composites. Sometimes it is better to tell that it is nano particle reinforced composites. Particulate composites are generally used to enhance performance at higher temperature. Particulate composites are not very fracture resistant, unlike fibrous composites. Particles tend to increase the stiffness of material, but do not have so much influence on composite strength. So, in this case matrix you can see it is having a particular shape, and in that the particle reinforcement is there and that is homogeneously dispersed along the matrix. Particulate composites can be further classified in 2 parts on the basis of orientation of particles. One is called the composites with random orientation of particles. Orientation of particles is randomly distributed. In this particular case you can see in all directions, example is the concrete, and composites with preferred orientation of particles. Particle orientation is aligned to a specific direction. You can see all are in a particular directions. Example, extruded plastics with reinforcement particles. Next, called the fibrous composites. They have fibers of reinforcing materials suspended in binding matrix. Unlike particles, a fiber has high length to diameter ratio. Further, its diameter may be close to its crystal size. These reinforcing phases may have random orientation, where they are randomly distributed in all directions, or may have preferred orientations where these are aligned to a specific direction. On the basis of fiber length, they can be further classified as short fiber reinforced composites, where generally the matrix reinforced by a dispersed phase in form of discontinuous fibers, generally length is less than 100 into its diameter. Composites with random orientation fibers, composites with preferred orientation fibers. And long fiber reinforced composites, they consist of a matrix reinforced by a dispersed phase in form of continuous fibers, either it may be the unidirectional orientation fibers or maybe the bidirectional orientation fibers. So, it is like a ply. Next is called the laminar composites. A laminar composite is composed of several 2-dimensional sheets or layers with different fiber orientations cemented together. Say for example, adjacent wood sheets in plywood are aligned with the grain directions at right angles to each other. You can see that all are present in the right angle. A laminar composites has relatively high strength in a number of directions in the two dimensional plane. However, the strength in any given direction is of course lower than it would be if all the fibers were oriented in that particular direction. A laminar composite often uses different materials in its layers to gain the advantage of combining the particular properties of each. So, generally we are calling it as a stacking. Types of laminar composites: there are three types of laminar composites generally found. One is called the conventional laminar structure. So, it looks like this: sandwich structure with foam core. So, we are having foam materials is in between. So, that is why it is called the sandwich structure, and last one is called the honeycomb sandwich structure. So, you can see that how the reinforcement has been placed inside it. Now, come to the testing of this kind of composite materials. So, testing of materials has got very much importance as it gives the required physical, mechanical and other properties for the use of that materials in given application. The quality assessment of the composites used in the specimens to be tested must be done prior to the testing whenever possible. If the composite used in the specimens is of low quality with defects, then the property measured are spurious. It can mislead the design and analysis procedure and result in a premature and catastrophic failure of the structure. Hence, the quality assessment of composite before it is used in specimen or actual structure fabrication is very much essential. The following quality assessment in composite is essentials like voids, broken fibers, delaminations, matrix cracks, and also the quality of bond between the fiber and the matrix. Now, first come to physical characterization of composite materials. Physical characterization is determination of all the physical properties of a given material such as density, fiber volume fractions, void content, coefficient of thermal expansion, heat conduction coefficients, moisture content, etc. Physical properties of the composite play an important role in the measured mechanical properties. There is a direct dependence of mechanical properties on the physical properties. For example, the mechanical properties are directly dependent on fiber volume fractions. Here we will consider the following physical property measurements like density, fiber volume fraction, void content, and the last one is moisture content. What is density? A material density is defined as mass of the material per unit of its volume, that logically we know. It is basically a measurement of the degree of compactness of a substance. One of the most common use of density is in how different materials interact when mixed together. For example, a wood floats in water because it has a lower density. Anchor sinks in water because the metal has higher density, and helium balloons float in air because the density of helium is lower than the air. The procedure for measuring the density of a composite material is same as that used for any other solid and is based on ASTM specifications D 792-86. Test procedure. The procedure consists of the following steps: weigh specimen in air to the nearest 0.1 milligram, attach specimen to analytical balance with a thin wire and weigh while the specimen and portions of the wire are immersed in distilled water. So, step 1, then step 2, and then come to the step 3, weigh wire alone partially immersed up to the same point as in the previous step. So, first in this particular case, weight of specimen in air, that is A, apparent weight of fully immersed specimen and partially immersed wire is B, apparent weight of partially immersed wire alone, that is W. So, the density of material at 23 degree centigrade can be calculated as follows: rho is equal to A by A plus W minus B into 0.9975, where rho is the density generally in gram per centimeter cube, A is equal to weight of specimen in air, B apparent weight of fully immersed specimens and partially immersed wire, W apparent weight of partially immersed wear alone, density of distilled water at 23 degree centigrade in gram per centimeter cube is equal to 0.9975 gram per centimeter cube. Next, fiber volume fraction. It is the percentage of fiber volume in the entire volume of a fiber reinforced composites material. A variety of methods exists for determination of fiber volume fraction, an important property of a composite. Generally, fiber volume fraction ranges from 30% to 65%. The lower end depend upon the significance of property contributions of the fibers, whereas the upper depends upon the effective defect free packing. Methods to determine the fiber volume fraction. There are 4 main methods to determine fiber volume fraction present in a composite. Number 1 is acid digestion method, number 2 is optical microscopy method, number 3 is the resin burning off method, and the last one is called the gravimetric relation method. First, acid digestion method. This method involves the digestion of matrix material using an acid which does not attack the fibers. Procedure: the matrix material is digested or dissolved by putting a measured volume of composite in an acid bath. Following digestions, the remaining fibers are washed, dried and weighed. Knowing the initial weight of the composite specimen as well as the density of the composite, volume of the entire specimen can be calculated. Thus, knowing the density and weight from step 2 of the fibers, the volume of fibers and the fiber volume fraction can be determined. One should be careful to choose the liquid for digestion such that the fibers are not digested. Generally, hot nitric acid is used for carbon epoxy composite. The STM standard used for digestion methods are D-3171-76. It has been started in the year of 1990 for polymeric composites, and D-3553-76. It has been invented in the year of 1989 for metal matrix composites. Next, come to optical microscopy based techniques. It involves spotting section samples of the laminate polished using standard metallographic techniques and obtaining digital cross sectional photomicrographs using an optical microscope and magnifications between 100 to 2500. Digital images may be recorded at a number of locations along the length and through the thickness of the laminate. Computer programs aid in the analysis of fiber ratio in the photomicrograph of the polished composite specimen. This method is preferred as a non-destructive approach to determination fiber volume fraction. So, you can see optical microscope of the cross sections of the carbon epoxy and the flax epoxy. So, here we can count the number of fibers are present in that particular area. Then third one, resin burning off method. This method applies to composites with a reinforcement such as glass or ceramic that is not affected by high temperature environments, or a reinforcement such as carbon when the temperature can be adequately controlled to minimize the degradation of the fiber during burn off. Test procedure: heat up the composite to a temperature at which resin will melt and fibers remain stable. After burning of resin, weigh the fibers. Now, the fiber volume fraction can be calculated from the initial weight of composite and fibers weight. So, simple, you have to separate the fibers from the composites. Next, gravimetric relation method. This method determines the density of composites and then calculates the fiber volume fraction knowing the density of the fiber and the matrix. When it can be confirmed that the composite materials has 0 or negligible less than 1% porosity, the fiber volume fraction can be obtained from the densities of the composite and the constituents by the following gravimetric relations, that is capital Vf is equal to rho c minus rho m by rho f minus rho m, where Vf fiber volume fractions, rho f is the density of fiber, rho c is the density of composite and rho m is the density of matrix material. Next, come to the void content. A void is a pore that remains unoccupied in a composite material. So, that means it creates some kind of hollow space inside the composites. A void is typically the result of an imperfections from the processing of the material and is generally deemed undesirable. Because a void is a non-uniformity in a composite materials, it can affect the mechanical properties and lifespan of the composite itself. Voids can act as a crack nucleation site as well as allow moisture to penetrate the composite and contribute to anisotropy of the composite. So, from the void itself inside the matrix, it can generate the crack, or maybe the moisture can come over there and it can deposit at that particular point. For aerospace applications, a void content of approximately 1% is appropriate for performance, while other grades of composites can have between 3 to 5% void content. So, you can see these all are known as the void between fibers, and these all are the voids in the matrix. Void content calculations: consider a composite consisting of fiber and matrix. Take the following symbols notations like VCFM volume of composites, VC, VF fiber, and VM is for matrix. Rho CFM, rho C is for density of composites, rho F for fiber, and rho M for the matrix. For composite with a certain volume of voids VV, the volume fraction of the voids VV is defined as capital V, V is equal to small vv by small vc. The total volume of composite small vc with voids is given by small vc is equal to small vf plus small vm plus small vv. By definition of the experimental density rho Ce of a composite, the actual volume of the composite is small vc is equal to small wc by rho Ce. By the definition of the theoretical density rho Ct of the composite, the theoretical volume of the composite is small Vf plus small Vm is equal to W small wc by rho Ct. Now, substituting equations 2 and 3 in 1, we have small wc by rho Ce is equal to small wc by rho Ct plus small Vv. The volume of void is given by small Vv is equal to small wc by rho Ce into rho Ct minus rho Ce by rho Ct. So, we can get this one. Now, volume fraction of the voids is this one, that is capital V, V is equal to small Vv by small Vc, which is nothing but the rho Ct minus rho Ce by rho Ct. In general, if void content is less than 1%, it is known as a very good composites. If it is more than 5%, then it is known as the bad or maybe the poor composite. Now, come to the moisture content. Moisture content or water content is the quantity of water content in a particular material. Composite materials, when exposed to the environment or water, absorb the moisture. Absorption of the moisture results in the expansion and affects the degradation of the mechanical as well as the thermal properties. Moisture content in a composite is given in terms of moisture by weight. Procedure to measure the moisture content, there are following steps, that number 1, a sample is weighed at the ambient conditions, then the sample is dried and weighed again. The average amount of absorbed moisture in material can be calculated as follows: m percentage is equal to Wi minus W0 by W0 into 100. So, m percentage of the moisture content, Wi initial specimen mass, W0 oven dry specimen mass. The difference in these two weights per unit weight of the dry sample gives the weight change due to moisture content. Now, what are the precautions we have to take? While drying, care should be taken to avoid excessively high drying temperatures and high thermal excursions that may induce thermal cracking, oxidations or mass loss or combinations of the three in the material. So, we should not raise the temperature too high. Wear clean non-linting gloves when handling specimens. Next, mechanical behavior testing of composite materials. In an effort to understand the mechanical behavior of composites at the microscopic level, a number of test techniques have been and continue to be developed. The principal aim of these tests is to evaluate the shear strength of fiber resin interface and any frictional effects that may be present. These micromechanical test methods fall into three categories. One is called the fiber pull out tests, fragmentation tests and the indentation tests. What is fiber pull out tests? The fiber matrix interface plays an important role in controlling the macroscopic mechanical properties of fiber composites, and it is often characterized by fiber pull out test. In this test, a single fiber is embedded in a thin sheet or film of a matrix material, and the force is required to pull the fiber out of the film is determined. Interfacial shear strengths are calculated using pull out forces for fibers with a range of embedded lengths. Pull out test procedure: a length of the fiber is embedded in the matrix. So, first we are having that matrix, we are putting the fiber over there, and then just we are trying to pull out that fiber from that particular matrix. Loading is applied at the free end and leads gradually to pull out of the fiber. The force displacement curve is recorded. Pull out test load displacement curve. Initially the load increases linearly with displacement. Matrix plasticity may lead to non-linearities. After a maximum load value, there is a sudden drop which lasts until the pull out of the fiber. The interfacial strength is defined as a function of the maximum load P max. So, generally tau is equal to P max by 2 pi capital R L, where P max maximum pull out load, small l embedded length and capital R is the fiber radius. The maximum stress on the fiber sigma max should not exceed its strength sigma Fu. So, sigma max is equal to P max by pi capital R square, which is less than is equal to sigma Fu. Now, pull out test other variations. One is called micro droplet test. This test include higher accuracy, simpler stress field of cylindrical symmetry and elimination of size effect. The embedded fiber length can also be easily determined. Another one is called the micro bundle test. So, this test is used to account for the high fiber volume fraction of real composites. Next, fragmentation tests. This test is developed from the early work of Kelly and Tyson, who investigated brittle tungsten fibers that broke into multiple segments in a copper matrix composites. Each test specimen for the fragmentation test consists of one fiber encapsulated in a chosen matrix and normally has a dog bone shape. So, you can see the shape, this shape is called the dog bone shape. Fragmentation test procedure: specimens are elongated in a tensile tester which results in fiber breakage. Experiment is done under a light microscope so that the fragmentation process can be observed in situ. The fiber inside the resin breaks into increasingly smaller fragments at locations where the fiber's axial stress reaches its tensile strength. When the fiber breaks in, tensile stress at the fracture locations reduces to 0. Due to constant shear in the matrix, tensile stress in the fiber increases roughly linearly from its ends to a plateau in longer fragments. So, first it will elongate, then after a certain time it will fall. The higher the axial strain, the more fractures will be caused in the fiber, but at some level known as saturation stage, the number of fragments will become constant as the fragment length is too short to transfer enough stresses into the fiber to cause the further breakage. So, in this particular case you can see the specimen with increasing number of fibers breaks due to increased strain levels in the matrix itself. So, this is the small LC is known as the critical fragment length. So, in this particular case sigma 3 is more than sigma 2 is more than sigma 1. So, stress in fiber as function of positions for the respective matrix strain levels. 0 stress corresponds to a positions with a fiber break. Calculation of interfacial shear strength. To derive interfacial strength, the stress field must be defined for constant shear. The average shear strength at the interface is given by tau is equal to sigma Fu into small d by 2 LC, where sigma Fu is the fiber strength at the critical length, small d is the fiber diameter and small lc is the critical fragment length of the fiber, the average fragment length at saturation stage, that is no more breaks occur when applying further strain to that particular specimen. Next, indentation tests. This test gives the knowledge about damage from concentrated out of plane forces, which is one of the major design concerns of many structures made of advanced composite laminates. It is performed on a grinded and polished surface. A flat square composite plate is subjected to an out of plane concentrated force by slowly pressing a hemispherical indenter into the surface. The damage resistance is quantified in terms of a critical contact force to cause a specific size and type of damage in the specimens. So, simple, you have to make a specimen over there which is polished and clean, and then after that through that indenter you are going to make a mark over there. The damage response is a function of the test configuration. Comparisons cannot be made between materials unless identical test configurations, test conditions, etc. are used. So, generally the indentation damage in composite laminates is look like this. Schematic representation of indentation damage. So, it is for the 90 fiber directions and right hand side related load displacement curve. These figures summarize the sequence of damage events observed in indentation tests along with its correlations with the load displacement curve. The load displacement curve is plotted using 4 different colors, each color corresponding to the damage mechanism represented in another figure of the same color. Then failure modes in micromechanical test methods. Specimen configurations and loading conditions determine the failure modes that may be present. So, generally test is pull out, specimen is the single fiber, load is the tension, interfacial failure, cohesive or abrasive, matrix yielding, fiber and surface loaded. So, generally the interfacial failure either it may be cohesives or adhesives, matrix yielding, fiber and surface loaded. Say suppose for micro droplet it is about the single fiber, tension, interfacial failure, matrix yielding, non-uniform loading. Say suppose for indentation, single fiber in composites, load is compression, interfacial failure or maybe the fiber crushing. So, not all the tests are appropriate for testing the properties of the 3 classes of composites, and the preliminary limitation of using a particular test is the fabrications of the specimen. In PMC, polymer matrix composites, specimens for all the tests can be made. For MMC, these are currently restricted to fragmentation and indentation tests. For ceramic matrix composites, these are confined to the indentation test because of the low interfacial shear stress in these particular systems. Now, we have come to the last slide of this particular lecture. So, in summary we can say that generally the composite materials, their types and applications we have broadly discussed in this particular lecture. The testing of composite materials has got very much importance as it gives the required physical, mechanical and other properties for the use of that material in given application. Several physical and mechanical property measurement methods have also been discussed in this particular lecture. These test methods are used for quality assessment during the composite materials development before it is actually used in applications. Thank you for your patience.